In this video, I'm going to be explaining end-to-end encryption and specifically the Diffie Hellman key exchange. This is the method of encryption that is used in many popular messaging apps such as WhatsApp, Signal, or Telegram. But one thing that has to be noted is they use much more complex encryption algorithms and there are multiple layers. I'm going to be talking specifically about the key exchange, which helps these private messaging apps to make sure that your communication or your messages are completely secure and are not readable even by the server. So the first thing that you have to understand is how it differs from traditional encryption methods, because even before messaging apps such as WhatsApp and Signal became popular, messages were still encrypted. Every time you open a browser, your communication with that server is still encrypted, but it's not considered as end-to-end encrypted. So before, what used to happen was your message would be encrypted on your side, it would be decrypted on the server before it was relayed to the next person, and then it was encrypted again and decrypted on that person's side. So the server was able to decrypt all your messages. So if the server was to get hacked or any government party wanted to have access to your data, it was definitely possible because they had the keys to decrypt the message. It was stored in plain text on the server. But end-to-end encryption, or E2E, changes that. So here only the people involved in the conversation have the keys which are used to encrypt and decrypt the message. So even if the server or the database stores or has access to your data, it's the encrypted or it's the encrypted data. They don't have access to the plain text, and they don't also have the keys in order to do that. But there's a problem with this, and that problem is, how do two people, maybe in different parts of the world, have the same key in order for them to encrypt and decrypt the data? So that's the problem which is solved using the Diffie-Hellman key exchange. So if the key has to be same, if two people want to engage in a conversation, they have to encrypt and decrypt the message. Both of them have to have the same key. But if they have to have the same key, it has to be sent over the internet. But if it is sent over the internet, it can be intercepted, and then a private person, outside person, could get access to your messages and decrypt them, so they are no longer secure. So the Diffie-Hellman key exchange is performed, and that's how we solve this problem. So this is a mathematical calculation that I'm going to explain in order for both parties to arrive or get access to the same key without ever exposing it to the outside world. So this is a basic diagram that I'm going to be using. So you have our server that's kind of like a middleman, is sitting in the center, and then let's assume we have two people who are trying to engage in a conversation. We have a client A and we have a client B. So if you take a messaging app such as Signal, it's completely free. It allows anyone to use its services for free. So let's take our Signal server. Now our Signal server exposes two different numbers or two different variables. These are public, they are accessible by anyone. So we have two numbers, one number called G and one number called N. Now G is usually a small number, it's usually a small prime number, and N is a huge number, it's usually 2000 bits or recently 4000 bits. Now the way the size of this number is decided is based on security and efficiency. So you usually want a larger number to increase its security, but after a certain point, the security no longer increases, but it just takes longer to encrypt and decrypt the message. So there's a sweet spot that you have to identify, and 4000 bits is usually the standard nowadays. Now this is happening on the server. Now when two people want to engage in a conversation on each of the devices, for example their smartphone or their mobile phone or their laptop, they randomly generate a large number, usually between 0 and n-1. Now this number is randomly generated and it's private. They just do this on their device and they don't share it with anyone. So client A might generate a random number A and client B might generate a random number B. So we have two numbers generated on each of the devices. Now we can't share A and B directly, but what we're going to do is we're going to use this number G from the server to create a new number. So client A is going to create a new number G to the power A, and client B will generate a new number G to the power B. So we have two new numbers which are calculated on both the devices, and this new number is going to be shared over the internet. So this number, we don't mind if it's exposed because G is obviously public already, but there's no way to find out A from this G to the power A, or find out B from G to the power B. That's almost impossible. So this number is shared over the internet. Now once it's shared, the next calculation is performed. So this G to the power B that client B had sent to A, we're going to raise this to the power A, the random number that client A had generated, and then we're going to do something called mod n or modulus n. Now this is unlike the common thing that we do in math. Modulus is a function generally used in programming where you divide a number by some number, and instead of getting the quotient you get the remainder. So if you divide 2 divided by 2, and then the remainder is going to be 0. So 2 mod 2 is 0. So that's what we're going to do. Now the reason we're doing this, generally modulus is used in all sorts of encryption or hashing functions, so that you take a huge number of unknown size and you shrink it down into one specific size that you know. So that's generally the reason we do it. So the client B sends a number G to the power B, we raise it to the power A, and we do modulus n. Now client B does the same thing but with G to the power A that client A had sent, and we raise this to G to the power we raise this to B, and then we do modulus n. So we have these two calculations being performed on either side, but mathematically if you see, both of these calculations give you the exact same number, because this is one of the exponent laws and it's just simple mathematics. So G to the power B to the whole power A is basically G to the power BA or G to the power AB. So you end up with the same number on both sides, and then we're doing modulus n. So this helps us shrink it down into one specific size. Now we've arrived at the same number. Now what we can do is we can use this as our private key to encrypt and decrypt our messages. So the Diffie Hellman key exchange is performed successfully and we arrive at the same number. Now any message that we want to send over to the other person, we can encrypt it using any encryption algorithm, but use this as the key. We send it to the server relays it, either saves it in a database or directly relays it to the next client, and the client decrypts it with this key. So the only people who have the keys to this encryption is the people who are engaged in this conversation and have performed the key exchange. So we have successfully done this. Now again, to reiterate, WhatsApp and Signal do use a Diffie Hellman key exchange. They're always used, and if you go over and see Signal's documentation, they actually perform a triple Diffie Hellman key exchange. So it is being performed. This is absolutely necessary, but they use multiple layers of encryption and the key exchanges in order to securely transfer your messages. So that wraps up this video. If you liked it, please leave a like and subscribe. And if you have any comments or want to see any future encryption videos or any other technology, please let me know. Thank you for watching.